Thanks a lot, Ariel, and thanks everyone for being here. As I mentioned, I've been here for the last week, in large part, and we'll be here for the rest of the week. So if people would like to chat sometime after hearing this talk, if you have any darts to throw, I'd be happy to receive them. Computational social choice is an area that I've just recently become interested in. And again, one reason I'm here is to interact with people like Ariel, like David Parks, like Jerry and Katie, and so on, to learn a little bit more about what's going on within the community. What I want to describe today, first of all, are two pieces of work that I've done that basically provide a very explicitly decision-theoretic model for a couple of problems in social choice. This is joint work with my PhD student, Tyler Liu, actually a very bright guy. You should keep an eye on him. But given my background in decision theory, I'm very interested in casting these two particular models in kind of a broader decision theoretic context. And in particular, what I'd like to do is position it within what I'd like to characterize as a fledgling research program that Tyler and I are beginning to engage in, that basically takes a decision theoretic lens, so to speak, and looks at a number of different problems within social choice, such as vote elicitation, manipulation, learning of preferences, things of that nature, and tries to bring that decision theoretic perspective to bear. All right? So let me get started. First of all, what is social choice theory? For many of you in this room, I'm sure you don't have to spend a whole lot of time talking about it, but basically we can think of it as the study of collective decision making. A little more precisely, the idea is as follows. Maybe we have some collection of individuals here. Uh-oh, something happened. What happened to my tennis court? Imagine that there's a tennis court right here. I have no idea what happened to the tennis court. Okay. Imagine that we've got a collection of individuals that have some preferences over potential outcomes or decisions that we could make that have to be made in a consensus fashion. Okay, for example, a city may have to decide between building a tennis court, maybe not, a playground, or a park, or a swimming pool, right? And there's only a budget to accomplish one of these tasks. What we'd like to do is somehow take into account the preferences of all the members of our population, of our target user audience, of our society, aggregate them in some way to determine an appropriate consensus outcome. This is obviously a very important problem. When we think about things like political representatives, committees, public projects, or even much more mundane things. And for that reason, it's been studied and discussed for millennia, and even formally for a large amount of time, for centuries even. Okay? So you might ask yourself, why do we care about computational social choice? Well, there are a few answers to this question. One is that the computational problems and models that arise in social choice are inherently interesting in and of themselves. Questions like the complexity of winner determination. How do we actually implement various voting rules in a computationally effective manner? Questions associated with manipulation. How do we ensure that people vote sincerely, or how hard is it for somebody to determine an insincere vote that might change the outcome of an election or a consensus decision-making scheme? How do we approximate any of these questions? And what are some of the computational and communication complexity questions, and what is the complexity associated with various of these problems, from winner determination to manipulation? It's also inherently interesting to people in artificial intelligence who study multi-agent systems. We're interested in building collections of agents that act autonomously on behalf of various individuals, and there will often be competition for resources, for example, network bandwidth, and we'll have to come to some notion of compromise or consensus in a lot of these situations. However, it turns out that, especially within machine learning and by and large across computer science, there's an increasing interest in preference aggregation. Basically, as the preferences of basically millions of individuals has become readily available, right? For example, if we think about web search, right? Every time somebody types in a Google search query, gets a list of 10 results and chooses one that can be viewed as expressing possibly an implicit preference for that result over the other 10 that are at the top of the search rankings. More explicitly, you've got numerous recommender systems in e-commerce settings, even in social network settings, where people are explicitly rating products, information sources under other individuals. Okay, so for example, excuse me for just 1 second. I see something has happened to all of my slides. I'm not sure what it is. If you just give me a second, half of the pictures seem to be missing. Your image cannot be displayed. Anybody ever seen this before? Okay, but I did this morning. What's that? This is my computer. Anybody ever seen this before? Okay. What's that? No. Yeah, they're usually embedded in the presentation itself. Let me just try it one more time. What's that? Sorry. That's what happened to the tennis court. What's this say? Okay. No? Tennis court's missing. What's that? Did the error message change? Okay. Okay. Well, you know what? I think I'm going to have to carry on, and you'll have to use your imaginations. Okay. That's a little. It's on a key in the office. We'll see what happens. Okay. We'll see how bad it is. All right. Okay, imagine a whole bunch of users here thinking about movies, all right? The question mark came through, right? It can display characters. That's good. Enough memory for that. Okay. Sorry, let's just backtrack. Let's just backtrack a little bit. The key point is that the ready availability of preference data, sometimes incomplete, sometimes implicit, has really made preference aggregation and social choice relevant. Okay, and the ease with which we're able to collect preferences. I don't know how many people are part of academic departments that are run by SurveyMonkey, but that seems to be a very common piece of software these days to gauge preferences and opinions. The ease of such communication has made it very easy to collect preferences. So what does that have to do with social choice, right? Just because we can assess people's preferences and we want to make recommendations of movies, books, friends on their behalf, or search results, what does that have to do with social choice? Well, increasingly we're seeing a tension between what I'll call personalization and aggregation of preferences. Obviously, organizations, companies like Google and Netflix are best served by personalizing their recommendations or their search results to the individuals involved. That's going to make them as happy as they possibly can be, right? Unfortunately, generally speaking, it's impossible to truly customize search results or recommendations to a particular user. Some aggregation has to be taken into account simply because, for instance, reasons of data scarcity. Right? Google does not know enough about Ariel's preferences to be able to say this is the search result you want when you express a particular query. So there's a lot of aggregation that happens. His implicit preferences will be aggregated with people of a similar type, for instance. and the results will be presented in a way that maximizes the satisfaction of those people that are similar to Ariel in some respect. Okay, and clearly some compromise and consensus has to be made. We can't just present every possible search result. When Google presents the top 10 ratings, maybe Ariel's preferred result is not listed among the top 10. Okay, so he's been sacrificed to the consensus good, so to speak. Okay, and this is happening a lot increasingly. There's a very hot area of machine learning known as label ranking, which basically does what I've just described in a very formal way. We assume we've got a user population, each characterized by a set of observable attributes, maybe their demographic attributes or their browsing history. We're going to segment these users based on their observable attributes, determine a consensus ranking, an explicit ranking for each of these segments, and make recommendations based on that basis. But little thought is given to the notion of consensus, especially from a social choice perspective, and very little thought is given to the decision criterion that is being used. What is somebody trying to accomplish when they produce such a ranking? Okay. So getting onto this point about coming up with the appropriate decision criterion, we've taken the view. We're not the only people who take this view, of course, but basically when we think about the application of social choice to computational problems in particular, we would argue that you should begin with an explicit articulation of your decision criterion. What is it that you're trying to optimize? What objective are you trying to attain? Okay? And then engineer particular social choice schemes or aggregation schemes that will optimize relative to that criterion, or at least analyze existing social choice schemes relative to that performance criterion. What are some of the advantages? Well, first of all, it'll allow us to trade off the costs of any particular decision or consensus outcome with the societal value, however we just decide to measure societal value. It'll make approximation very obvious, and for a lot of people in this room, approximation is a fact of everyday life from a computational perspective, but it's also going to be important from an informational perspective. We're often forced to make decisions with incomplete information about a user's preferences. And this is a point I'll maybe discuss a little more at the very end of the talk. Okay? It may give us a more nuanced analysis of things like manipulation and incentives, something that, again, I'll try to dwell on just very briefly at the very end of the talk. And it can make learning and elicitation of people's preferences much more effective, right? By having a decision-driven loss function rather than a predictive loss function, which is the norm in machine learning and in learning to rank, we can often get much more effective results, come to much better outcomes with much less data about people's preferences. Okay? So let me illustrate with a couple of examples. Okay? So we actually got interested in social choice through the following question. Right? Why is it that you would want a consensus ranking? In social choice, there are basically two problems that we try to address. One is given some alternatives, what is an appropriate consensus outcome? In other cases, we're interested in a consensus ranking, something that aggregates everybody's preferences into some representation of societal preferences, so to speak. Okay? But you might ask yourself, why should we care about rankings? Why would we want to produce a societal ranking as the output of some social choice rule? Okay? Well, there are a handful of answers. One is that we don't if all we want to do is produce the right public project. Okay? We want to choose a single park, recommend a single movie to somebody. Okay? It doesn't make sense to have to produce an entire ranking. You're only going to use one. Of course, in some situations, you may actually use or consume or somehow work your way through an entire list of alternatives. So maybe you might want a consensus ranking. Third answer is the following. Maybe you choose an alternative. You collect people's preferences. You choose an alternative. Okay, but when you're about to act on that alternative, it becomes unavailable. Okay, if you had a consensus ranking it would be nice to be able to go down the list and say if the first alternative becomes unavailable, I'll go to the second. If the second is unavailable, I'll go to the third, and so on. All right? And this is one model that I'm going to talk about today. It's called the unavailable candidate model, which, for a situation like this, the idea is that it'll produce a suitable notion of consensus, of a consensus ranking, when we know that alternatives are going to become unavailable with some known probability. Okay? A fourth answer is that not that alternatives may go missing, but you may be able to consume more than one of these options, but there's a limit. Okay? Maybe we can build K parks and tennis courts and so on, and we have to decide which K, right? Or we can recommend 3 movies, or we can present the top 10 search results, but no more. Which 10 should we present to our user population? Okay? Which members should we elect to a committee of size K? Things of that nature. Okay? And this is a second problem that I'll talk about, which is a budgeted social choice model. Right? One way to think about it is if you gave me a list of societal preferences and ordering, then I could pick the top K from that list and say that's a good recommendation. What we're going to do is develop a model that maximizes societal satisfaction given this slate of K alternatives, and show that, in fact, it may be very different than actually picking the top K from using normal notions of consensus. And this model is going to allow us to explore the trade-offs between the cost or the size of that recommendation set and the degree of societal satisfaction that one gets. Okay, so just by way of overview, I'm going to give a very, very brief introduction to social choice proper. I think Ariel was in the room just around here giving the same kind of introduction on Thursday. I would defer to that talk for those of you who were there for a much more concise, I shouldn't say concise, a much more detailed and motivating introduction to the problem. And then we're going to talk about our 2 models, the unavailable candidate model, which, by the way, was independently proposed and developed by Jerry and Katie, who are here in the room, and I'll make maybe 1 or 2 points of comparison as I go through. I'll talk about, as I develop the model, talk about computations and approximations of the optimal ranking under this model, and talk about connections to existing social choice schemes. Okay? Then move on and talk about our budgeted social choice framework. This has some very strong connections to work that's gone on in computer science. One class of problems known as segmentation problems, which in fact can be viewed as a way of approaching social choice, although Kleinberg et al. Do not talk about social choice problems. They think more generally about combinatorial optimization. We'll argue that this is actually a good way to think about trade-offs in social choice. Okay? Of course, there is very much related work in the social choice literature on things like proportional representation and multi-winner elections, and I'll mention a few of those connections, talk about connections to top K methods, and again, spend a little bit of time talking about computation. And then I'll just wrap up with 1 or 2 slides on some of the other advantages of the decision-theoretic perspective. Okay. And my guess is my tennis court's going to be missing here too. Oh yeah, look at that. Okay. All right, so the tennis, and in fact the tennis court was supposed to be the winner. Ah, gee. Okay. Anyway, so what is social choice, right? The general framework which is going to underlie everything that follows in the talk is as follows. Imagine we have a set of alternatives or candidates that we need to select from C1 to CM. We've got a set of voters or users, a population that we're trying to satisfy, 1 through n, each of which has preferences over this candidate set. The preferences are going to be represented by simply a linear ordering or a permutation of that set C. We'll call our users voters, and we'll call their preferences a vote. Right? Simply sticking with standard social choice terminology. A profile is simply a collection of votes. Okay, so this would be a profile here if the tennis court and these other individuals were actually showing up. All right, so we have this dog owner who would prefer a park to the mythical tennis court, to the swimming pool. Somebody else here would like the swimming pool over the tennis court, over the park, and so on. Okay. And there are two possible aims, as I mentioned. We might want a consensus winner, in other words, an alternative that, choose an alternative, say a public project, that maximizes some notion of consensus or user satisfaction, okay? This should show the mythical tennis court right here, all right? Another thing we might want to do is produce a consensus ranking, as we've already mentioned, where we produce a ranking that represents societies or our user base's preferences over the alternatives in some consensus fashion, okay? And again, we would hope that if the tennis court were the maximizing choice, it's at the top of the consensus ranking as well, okay? There are a number of common voting rules that people have used to pick consensus winners. Just very briefly, a very common one that you're all familiar with is the plurality voting rule, which picks, excuse me, which picks the winner C that has the largest number of first place positions among the votes V. The nice thing about plurality is that voters needn't provide a full ranking. You'd also say that's the nasty thing about plurality, right? There's no nuanced notion of preference. Another common way of doing things is using positional scoring. We assign a score alpha to each one of the rank positions in a way that's non-negative and non-decreasing, the board account being a very well-known version. So if you rank the playground first or the park first, that will get a score of 3, the tennis court a 2, and the swimming pool a 1. And then for each candidate, we would simply sum the scores derived in this way from each of the votes, and the winner would be that candidate that has the maximum sum of these scores. Okay? And grayed out here, there are a whole variety of other voting rules, right? Entire books filled with potential voting rules and courses given on such. When we talk about rank aggregation, rather than just picking a winner, there are a number of methods that one can use. Again, it's impossible to begin to enumerate them here. First, we note that any scheme that scores candidates could be used to produce a ranking. For instance, if we use board of scoring, we could rank all of the alternatives by their total board account or their total board or positional score. More interesting is a notion that I'll use a little bit later, which is the Kemeny consensus, which is a very well-known scheme. The basic idea is, and there was, boy, I apologize for this. There's all of these pictures have gone missing. Okay. And even the error message is missing now. I have no idea what happened. Shouldn't have restarted. All right. And anyway, the Kemeny consensus is pretty straightforward. You know what? This is going to be a problem because these are formulas that have gone missing. Just give me a second. You know what? Why don't we try a different machine? Yeah. Oh yeah. No, there are formulas that have gone missing. It's probably easier to put it on a key. Sorry about that, everybody. That's a new one on me. What's that? Ah. Okay, thanks. What's that? Ah. Yeah. Yeah. No, hang on. I'll do a shortcut. Not yet, not yet. Okay. Let's just give it a try. No. Go down. Down here. No, same thing.
When you created this, I guess it might have embedded.
This. It was here as of this morning.
Were the pictures located on a different folder and not embedded in the?
No, they should have been embedded in the presentation. That's not what it's saying, is it?
No, it says that it cannot. Well, the error.
No, what did it say?
The image part with the relationship was not found in the file.
Yeah. You're kidding. Yeah.
I mean, it's not.
No.
This is looking for a file that doesn't exist, I guess.
Okay. Yeah, embedded. Not even Office format, PostScript format, like PDF, cut and pasted PDF, which has disappeared. Sorry, all the Office equations are missing. Yeah, it's gonna slow things down. I mean, one other option, I had an old version on a stick upstairs, which I can check. I can check. I apologize for this, everybody. This is a new one for me. No idea what happened.
You can try restarting while you're getting a new thing. It might, maybe some of the file references are. Do you want to look for the other USBs?
No, let me try it. It's just up in my notes.
The range of problems which is embedded for my project.
You know where that file is?
Let me see.
I've never, it's completely bizarre. It's there. All right. We'll run it from the memory stick. Okay. Should I go back and show you all the beautiful pictures? What's that? All right. Sorry, everybody. Thanks for your patience. That's completely bizarre. I've never experienced that before. If anybody has and has solved it before, let me know. Okay, in case it happens again. Okay. Where were we? We're talking about rank aggregation. Very briefly, the notion of a Kemeny consensus, which is something I'm going to refer to a little bit later in the talk. It's a very well-known scheme for measuring distances between rankings and coming up with a consensus ranking. Basically, we have a distance measure between rankings known as Kendall-Tau. Intuitively, it's very simple. We look at a ranking R and a ranking V or vote V, and we say that they disagree on two candidates, C and C prime, if one of them puts C above C primed and the other puts C primed above C, and the distance between two rankings is the number of pairs on which they disagree. A Kemeny consensus for a particular vote profile V, oh, we need to put this back in. Okay. A Kemeny consensus for a particular vote profile V is simply that ranking that minimizes the sum of these distances over all the possible votes. Okay, so it has fairly natural interpretation as trying to minimize the number of candidates that need to be inverted in the voters' ranks in order to reach consensus. Okay. Other notions, in the interest of time, I'm going to skip this. I'm sure probably people are familiar with the notion of Condorcet winner. I'm going to try to accelerate a little bit here. Okay. All right. The very simple, very brief primer in social choice. Okay. Now let's come back to this question that we already talked about, which is why rankings, right? Why do I want to produce a societal ranking? Okay. Well, let's explore one of these reasons, which I'll call candidate unavailability. So think of it this way. It works a lot better with the pictures. Suppose we have a hiring committee that are evaluating a set of job candidates for your favorite university, like the CS department at Harvard. All right. How they once they come engage in their deliberations, they may all have their own individual preferences, and we might have some preference aggregation scheme. Maybe they all vote somehow. We aggregate those preferences to come up with a winning candidate, somebody they'd like to make the offer to. Okay, but if you're a very hot candidate, like somebody we know who'll be on the market later this year, there's a question. Will the candidate accept the offer? Maybe they'll go to the University of Toronto. Heaven forbid. All right? Well, what should you do in that case? Well, it would be nice, for example, if we actually, instead of picking a winner, had a ranking that we could then use as a selection policy. So suppose this were the ranking of alternatives, then the committee would make the offer to the first candidate. If he went to the University of Toronto, then they'd make the offer to the second candidate. If she turned us down, we'd make the offer to the third candidate, and so on. Okay? So it would be nice to have a consensus ranking. So we've developed something called the unavailable candidate model to formalize just this intuition. Okay? As I mentioned, this is a model that was developed independently by Katie and Jerry. It's really quite simple to describe. As before, we're going to have a set of candidates, a set of voters, and a vote profile. In addition, we're going to have a distribution P over the possible subsets of S. Basically, P of S denotes the probability that S is exactly the set of candidates that are available when it comes time to make offers. Okay? Since we don't know which candidates are actually available at the time we're aggregating people's decisions, we can't just pick a winner. Instead, what we need is a policy, right, or a choice function that'll take any non-empty subset of our candidates and select a winner. Okay, so no matter what situation we end up facing, we know who to make the job offer to. Okay. Now we could imagine arbitrary policies, but of course we're going to consider something called a ranking policy, a policy that, like in the example that I described, policy that can be represented by a particular ranking that we can go down in order. The basic idea is, given an available set S, we'll simply choose that candidate that is the top in that set according to our ranking, right? One way to think about this is as a rationalizable choice function. It's a choice function or a policy that represents a quote-unquote rational set of societal preferences, okay? Now, as we're going to see, such a policy needn't be optimal. We can do better than a ranking, okay? But it has certain advantages. First of all, it's very compact. We don't have to represent an arbitrary mapping from subsets to candidates. It's very easy to interpret, very easy to implement, right? And in many cases, we could be legally or procedurally required to produce a ranking. So, for example, in the National Residency Matching Program, where hospitals get together and resident fellows get together to decide where residents will go to do their residency. Hospitals are required to submit a ranking of their candidates representing their preferences. But of course, hospitals aren't individuals; they're institutions. So that preference ranking actually represents some aggregation of the parties involved. Okay, so there are reasons, procedural reasons, for example, that we might want such a ranking policy. Finally, another interpretation of this is just as a rationalizable approximation to the optimal policy. Okay. So if we talk about it not being optimal, we have to say what we mean by optimality. So we'll measure the quality of a particular policy in terms of the number of disagreements that it will induce, right? And what do I mean by a disagreement? Well, we're actually going to focus our attention on first preference disagreements with the chosen candidate. In other words, in expectation, given this distribution over the available subsets, what is the expected number of disagreements, where by disagreement I mean a particular voter, the policy will choose a particular candidate from the available subset, and a voter will disagree with that choice. There will be another available candidate that they would prefer. Okay? Very, very intuitive notion. Just to illustrate, for example, if this is our consensus policy represented as a ranking, and this is some arbitrary voter, if candidates A and E are available, then we have a disagreement because the ranking, the policy will select A, but the voter would want E. Okay? But of course, if A were available and E weren't available, then they would agree. We'd have no disagreement. If A, B, and E, these candidates were unavailable, and again, we would again have a disagreement. Policy would say C, the voter would want F, but if F were unavailable, then we'd be back in a state of agreement. Okay? So what is the probability that will happen, summed over the voters? Okay? Now, I just want to make clear, this notion of disagreement is not the only one that we could use in this model. Okay? You could imagine positional scoring or board account. You could imagine approval or veto scoring, a number of other measures to get more nuanced notions of how dissatisfied or how much a voter disagrees with the policy. Okay? But all of our analysis is just going to focus on this simple notion of first preference disagreement. Okay? One thing to think about is how this differs from that Kendall-Tau metric or, that induces the Kemeny consensus. And intuitively, what happens when we're comparing the distance between our consensus ranking and what a particular voter wants, Kendall-Tau is going to take, say, a misordered pair like A and E. Here the ranking puts A above E. E is way down here somewhere. And this voter wants E before A. Okay? It's going to count as part of the distance or the disagreement this misordering of A and E intuitively the same as the misordering between C and F, where again there's this reversal. For most reasonable distributions, the probability of disagreement in our model in a case such as the policy says chooses A, but the voter wants C, is generally going to be larger than the policy outputting C, but the voter wanting F. Okay. So what's happening is that the Kendall-Tau metric and the Kemeny consensus in particular kind of ignores the relative importance of a mistake. Okay? In our case, our cost is going to focus more on minimizing mistakes near the top of voters' orders and care less about minimizing them at the bottom of of a voter's ranking. Okay. All right, so what is the optimal ranking? It's pretty straightforward. We simply want we want the ranking that minimizes the expected number of disagreements, as I've said. Okay. We're going to look at this for a very simple distribution P, where I fix the probability P that any candidate will be unavailable and they'll become unavailable. Their unavailability is independent. Okay, so we're going to flip a coin for each candidate. Okay, and I don't want you to bother reading this expression. This is why I didn't want to write things down on the board, by the way. Don't bother reading this, but it's just to show you that in this case, there's a nice closed form for the expected number of disagreements, and it illustrates that candidates lower in the ranking, under this model in particular, are going to contribute less to the expected number of disagreements. Okay? Now let's look at some connections to existing voting rules. All right? First of all, with respect to plurality, the optimal policy for this particular notion of disagreement is in fact what we would call the plurality policy. Okay? Give me a set of candidates S. I should just run a plurality vote and take the and select the plurality winner. Okay? This is just a consequence of our measure of disagreement, okay, which focuses on this first place preferences. Okay? Turns out that the optimal ranking may not be an optimal policy. Okay? For example, here's a set of votes, the votes associated with the Condorcet paradox, in which any ranking according to our measure will be optimal, say A, B, C. But of course, if A and C are the subset available, the plurality winner, the thing that minimizes disagreement, is C, right? Because C beats A twice in pairwise votes, but our ranking would say choose A. Okay? So we can be suboptimal relative to the optimal policy. Of course, if P equals 0, which is why we don't really consider that case, that means all candidates are available, then the optimal ranking policy will, in some sense, be plurality-based. We'll always put the plurality winner at the top of a ranking, and then we can order the rest of them arbitrarily, the rest of the candidates arbitrarily. Okay. In the interest of time, given our delays, I'm not going to talk about this other than to say that this ranking method need not put a Condorcet winner at the top of an optimal ranking. This is something that Jerry and Katie pointed out in their work as well. But if there is a majority winner, it has to be at the top of the optimal ranking. Connections to Kemeny, right? We can think about Kemeny as a decision policy as well. We can work our way down the Kemeny consensus. And we can ask ourselves, how well does Kemeny perform with respect to our disagreement measure? Okay? Well, in general, it'll perform quite poorly. In fact, it can be up to a factor of 2 worse than optimal in terms of the expected number of disagreements. Okay? Here's a simple example. Again, in the interest of time, I'm gonna skip through it. But the key thing is to note that in this example, as we increase the number of voters and decrease the unavailability probability as it approaches 0, as more and more people become available, okay, it's more likely that everybody's available, it's not too surprising that Kemeny will perform poorly in that measure, okay, because it is trying to get the entire ranking correct, even though you're never going to have to make offers to candidates deep down in that ranking. Okay? Excuse me. But the flip side of this intuition is that as P approaches 1, it means most candidates are going to be unavailable. Okay? So we're going to have to work our way deep down into the list in expectation until we find somebody willing to accept our offer. Okay? And in that case, it does seem more important to try to get all of the relative pairs correct. Okay? And it turns out we can show that as P approaches 1, okay, simply we have to make P large enough as a function of the size of the problem, the number of winners and the number of candidates and the number of voters. We can show that any optimal ranking, in our sense, is in fact a Kemeny consensus. It needn't be the case that any Kemeny consensus for that vote profile is an optimal ranking, but it turns out, okay, so there are going to be more Kemeny consensuses, so to speak, than optimal rankings. But any Kemeny consensus has an expected number of agreements that is a very small factor, very close to being optimal, right? Where a factor of 1 plus epsilon, where epsilon depends on the size of the problem and the particular probabilities, okay? So in some sense, we can think of this particular aggregation rule as encompassing a spectrum ranging from plurality voting when p equals 0 all the way up to the Kemeny consensus ranking when p approaches 1. Okay? And in some sense, you could think of this as justifying the use of Kemeny under certain conditions, okay? Especially when in this model the probability of unavailability is pretty high. Okay? In terms of computational optimization, that's the next question we'd like to ask. It's not hard to show that computing an optimal ranking is NP hard. This is simply because of the connection to Kemeny and the NP hardness in general of computing the Kemeny consensus. From a practical perspective, you can formulate this as an integer program, and I put practical in quotes because you can do it, but it really doesn't scale to problems of any significant size, even using state-of-the-art solvers. But you can devise a very good greedy algorithm that has some performance guarantees and works incredibly well empirically in at least certain classes of distributions that we've preferences that we've looked at. The greedy algorithm, let me just give you the brief intuition. There's a recursive decomposition of our scoring function, the expected number of disagreements that I won't get into, but I'm going to define a measure, dk, which is just the distance between our consensus ranking and the vote profile, or expected number of disagreements, conditioned on the fact that the kth ranked candidate in our ranking R is the top available candidate in R. Okay, so nothing in positions 1 through k minus 1 is available. Okay? The nice thing about this metric is that it doesn't depend on the elements that occur later in the ranking. Okay? So that means we can compute the score very effectively and optimize it against it very effectively. Okay? So what we're going to do is put in the first position, we're going to consider which candidate would be best if I assuming it was available, okay, would minimize the number of disagreements. Okay? Then what I'm going to do is I'm going to fix that candidate, call it R1, and then I'm going to look at, well, who would be the best candidate in the second position given that I fixed R1, okay? Not worrying about who comes later, okay? Once again, assuming that this candidate will be available, and so on, okay? And there are various tweaks and hacks you can do to this algorithm, all right? We get an approximation ratio here, of course, where we're looking at the performance, the expected number of disagreements of greedy relative, expected number of disagreements for greedy relative to the optimal ranking. Of course, this is going to be 0 only if we have strong unanimity, which means every voter has exactly the same ranking. Otherwise, there's going to be at least one disagreement with some probability. And if that's the case, if we have strong unanimity, Greeny's going to find the optimal ranking anyway. So we've got an approximation ratio here of 1 plus p squared over blah, blah, blah. And this works very well it looks pretty good for small p, say in the order of 0.25 or below, which will give you about a 2 approximation. Okay? For larger p, it's probably not acceptable. Okay? I believe it's actually quite loose. But despite the looseness of the bounds, even for large p, empirically, the greedy algorithm works very, very well. Okay? So just to give you a sense of that, we've done a number of experiments, which are showing one illustration, where we look at the performance of the greedy algorithm as a function of different problem sizes, ranging from 4 up to 9 candidates and 20 up to 45 voters. These problem sizes are small because we want to be able to compute the optimal. Okay? When we run the greedy algorithm, this is just a histogram showing how many instances out of 20, showing the degree of approximation, the histogram over the 20 instances of each size. So for example, for these small problems, you're always optimal. Okay? Here, you're almost always optimal, and so on and so forth. Okay? Notice that these are very, very close to being optimal, all within 0.5%. Okay? And these are for placket-loose mixture distributions. Oh, yeah, right? So now, these are not random in the sense of social choice, uniform, impartial, or impartial culture model or anything like this. These are distributions that people who involved in psychometrics, for example, think are reasonably plausible. And this is a point actually I want to talk about near the end of the talk, right? What are reasonable distributions to be able to evaluate some of these things? Okay. Okay. Anyway, the key point is I'm not going to let me not spend much more time on this. The running time of the greedy algorithm for problems of this size, it's instantaneous. Okay. There's even an even simpler algorithm that has faster running time, slightly worse approximation, and of course the optimal solution is much, much slower. Okay, the empirical approximation ratio, so to speak, shows little sensitivity to M and N, at least that we've been able to find so far in our limited experimentation. But of course there is sensitivity to P. Okay, as P gets larger, the greedy algorithm, of course, is going to do worse and worse because it's focusing its attention at the top of the ranking. Okay, but still, again, it's always under 1%, even for very large P. The other thing that we've noticed is that the Kemeny consensus computationally actually does pretty well for large P, which would conform with the theorem that we have saying that this converges to Kemeny. Okay, it doesn't do very well for smaller values of P. Well, it does okay, right? But it's almost always optimal or near optimal for large values of P. Yeah. Yeah.
I guess so. Like you said, you can see this as a spectrum where somehow plurality gives very high weight to disagreement in the first place.
Yes, exactly.
And Kemeny gives uniform weight in every disagreement.
Exactly. Yeah.
The question is whether for an intermediate P you can somehow take a version of Kemeny that gives higher weight to higher weight.
So people have, we haven't looked at the connections deeply. People have proposed weighted versions of Kemeny in the literature. How this is connected, I can't say off the top of my head. Yeah. I think right. I think you could, depending on P, if you set the weights appropriately, you could get a good approximation to this. Absolutely. So, yeah.
So in my reading, like the greedy seems to capture models reasonably well the way hiring committees
Probably.
operate.
Having been on both sides of this this process, as you have as well.
And is there anything? Is there any natural function that it is optimizing? I mean,
That greedy is optimizing? That's a good question, right? I mean, in some sense, we're making choices, making certain assumptions and conditioning on those assumptions, right? So we're saying, let's assume the first guy's going to be available, right? Who would I put in place to minimize disagreements, okay? You could take this chain of reasoning, possibly, and put together an objective function, right? But I won't swear that that's actually, say, mathematically accurate. It's just an intuition, right? Okay. Any other questions? By the way, feel free to interrupt, even though we're I used up probably a lot of question time. I'll skip over a few things. Okay. And finally, in the interest of time, I'm not going to, this is something I'll skip over. We also have a polynomial time approximation scheme. The greedy algorithm gives you an approximation ratio that's a function of of various properties of the vote profile and the setup. A polynomial time approximation scheme will basically say, give me any desired accuracy, and I would like, say epsilon, and I would like to produce, I would like an algorithm that will produce that'll run in polynomial time that will produce a winner, consensus ranking that's within that factor of being optimal, okay? But it has to be polynomial time in 1 over this precision parameter. And it turns out that's pretty easy to do. The intuition is simply to get the top positions, the top k positions right, and you can set that you can set k as a constant that depends on your desired epsilon or accuracy. Okay, so let me just skip over that. Okay, so just to summarize, and then I'll spend try to go through 15 minutes of the budgeted social choice model. Just to summarize the unavailable candidate model, it's one way of justifying the use of consensus rankings. It sets out a particular decision problem where ranking can be used for a particular purpose. It's decision theoretically motivated. Although our analysis is focused on a very specific scoring metric, there are the framework can be generalized to other notions of disagreement, strong connections to existing voting schemes, and has some nice computational properties. In terms of generalizations, this is why this is a backup slide. It's not quite right, but we've looked at other classes of distributions. In fact, we have what are very crude bounds for arbitrary distributions. When it comes to the greedy algorithm, we can say this is how well it will perform. Whether or not you can do it tractably is another issue. It depends on properties of the distributions. So in terms of general exchangeable distributions, something that Katie and Jerry studied in depth in their work, it turns out that our greedy algorithm is adaptable, can run in polynomial time. Notice that our distribution is a very special case of an exchangeable distribution. Shouldn't say some of the complexity, some of the analysis of the bounds transfers, but the bounds are a little bit looser. We've looked at things like graphical models such as Bayesian networks and how to apply the greedy algorithm then. And then there are a number of other issues that we're very interested in, such as more sophisticated disagreement metrics, measuring how far from optimal this ranking policy can be relative to the plurality policy or other policies. Okay, and an interesting question is that of incentive issues, right? What happens? What are the incentives to misreport one's preferences in this scheme? But there's this added wrinkle of subjective probability assessment. For instance, when we've got to assess candidate unavailability, maybe you're actually asking the voters themselves to provide some estimate of candidate availability or unavailability, right? What does that do to the incentives? How can they manipulate our voting scheme, our consensus aggregation scheme, by misreporting those probabilities or those estimates? All right. Very briefly then, I'm just going to close this door. Very briefly, let me talk a little bit about the budgeted social choice model. Again, by returning to this question of why rankings, right? Why is it that you'd want a consensus ranking than just a decision? And one reason that we want to explore is suppose you'd like to make everybody happy. Okay, you'd love to engage in personalized decision making, provide everybody their best possible movie or web search result or public project, park, swimming pool, tennis court, but you've got constraints, right? There's a limited budget that you can spend on public projects, limited amount of screen real estate when it comes to returning search results, things of that nature. Okay, you can tell the age of my child and probably the gender by the selection of movies here. So as an example, suppose a whole selection of new releases, video releases come out this month, and your Netflix or Blockbuster, or I guess you can't be Blockbuster anymore, but a local video store or a video on demand provider, Comcast, Rogers in Canada, something like that. And for whatever reason, maybe inventory constraints, budgetary constraints, what have you, you can only acquire 2 new releases. Which 2 should you buy or make available to your customers? Well, an obvious thing to do would be to look at your target population of 6-year-old girls and ask yourself, how do I make them as happy as possible, right? You want to make them happy because if they're happy, you're probably going to make more money, okay? So a natural thing to do would be to collect their preferences, aggregate them into some consensus ranking, okay? And then pick the top 2 items in this ranking, stock them, and make yourself a lot of money, keep your users satisfied, okay? So this is a very natural phenomenon. very often we would like to do this personalized decision making, but there are constraints on the alternatives that you're able to provide on the set you can make available to your target population. In public projects, there may be budget limitations on the number of parks you can provide within a city, logistical limits on the number of bus routes, things of that nature. In committees, you know the saying, any committee of size greater than 1 is too big, right? Well, there are logistical limitations on the sizes of your representative bodies or your committees that you want to put together. Talking about product configuration and recommendation, again, maybe inventory limits, production limits, budget limitations and things that limit what you're able to do, okay? So it'd be nice to have a ranking and choose the top K. But what we're going to see is that producing a consensus ranking using standard techniques and choosing the top K from that consensus is often a bad idea, right? Intuitively, consensus rankings are going to put more popular items near the top, okay? And not going to focus on the notion of diversity among diversity with respect to the range of user preferences, okay? Which is what we'd want in a representative body or selection of alternatives we make available to our population, right? So to formalize this, what we need to do is, again, articulate a decision criterion or an objective function to define what we mean by an optimal set of alternatives. And this is what the budgeted social choice model does. It's a framework, basically, for trading off the cost of a set of alternatives with the benefit that our user population derives from it. One way to think about it, there's huge literature on multi-winner elections in social choice. This is one way of kind of generalizing multi-winner elections to account for these types of trade-offs, as we'll see. Okay? So for example, the ingredients that we need to do this, first of all, we've got to assign a budget to a choice problem. We might say, I can't have any more than 5 committee members, or I can't spend more than $1 million on new parks this year within my city, or I can't have more than 3 product lines this year, and I can only produce 10,000 units of each. Of course, if we've got a budget, we have to have a cost. What does a quote-unquote set of alternatives actually mean? Or what does it actually cost? They put set in square quotes for a reason that'll become evident in a moment. We've got to define a social objective. What value does our population obtain from any set that we provide? For instance, are we concerned with whether a voter's preferred item is available, what the ranking of the best item in the set is? Do they have some approved items? How many items are they happy with? Things of that nature. And then, given these things, our goal is going to be straightforward. Find a set or a consensus slate, for example, that maximizes the social objective but doesn't exceed our budget constraint. Okay? Now, we could get away without a budget, right? We might say, hey, maybe I just want to trade off the cost of a set of alternatives with the social benefit, right? And blow the budget if I'm going to really improve my user happiness. And that's a reasonable thing to do, but I'm not going to explore it here, okay? But it's an interesting thing to think about in social choice. All right, so what is the basic model? Okay, and this will be familiar to some of you because it'll look like a number of other models in the computer science and the social choice literature. Okay, first again, we're going to have a set of, I'm going to call them alternatives now rather than candidates, set of voters or users. Sometimes I'll call these things items, and a profile again. I'm going to assume that there's a fixed cost, TA, for every alternative A that I might make available to my user population. For instance, if I consume a spot on a committee, if a committee member will consume a spot on a committee, a search result will consume a spot on a web page. It will consume some valuable screen real estate. There might be some costs to configuring an assembly line, acquiring rights to a movie, et cetera, et cetera. Okay? There's going to be a unit cost for each item as well. Okay? So I don't just have to produce, get ready to make that alternative available. There may be, for instance, a usage cost. Every time somebody uses my park or my highway, there might be a cost associated with it. Every time somebody consumes a product of a particular type, there might be a cost associated with it. Okay? All right, so intuitively, I think that's pretty clear. Okay? And our budget B is basically the maximum that we're allowed to spend on our set of alternatives. Okay? But of course, we can't just produce a set of alternatives. We can't just say, here's a set, users go ahead and use it as you see fit, partly because, well, exclusively because of these unit costs, right? Everybody might gravitate towards the most expensive alternative, and we could blow our budget. So instead, what we need is a recommendation function, simply something that assigns an item to each one of our voters. Now, there's an implicit assumption here that each voter is deriving benefit from one item. Could be generalized. We could have set-based preference functions, but I'm going to keep it simple. Okay? This doesn't mean voters can't be unassigned. We could have a zero-cost dummy item. That would be fine. And I'm going to denote by phi of n the set of items that are assigned to at least one voter. Right? So if I am giving you a particular copy of this movie, then I've got to acquire the rights to that movie if I'm Netflix. Okay? Just an example. So these little girls are going to get High School Musical. These girls get to watch Tinkerbell, and these sad little girls don't get to watch anything. Okay? We're going to say that the cost of a recommendation function is simply the sum of the fixed cost for anything that I recommend times plus the sum of the unit cost, depending on how many people I actually recommend it or assign it to. Okay? Now, how do we measure societal value? How good is a recommendation set? Okay, well, we're going to use positional scoring, assuming a scoring function as I've already described, for instance, Borda scoring. And I'm going to measure user satisfaction with the item to which they've been assigned as their Borda score, right? So the higher up it is in the ranking, the happier they are with the item. Okay? So if this little girl is assigned High School Musical right here, then she's going to derive a benefit of 2. Okay? And we're just going to sum these user scores to determine the quality of a recommendation function. Okay? Our objective then is pretty straightforward. Maximize the sum of these scores subject, given this recommendation function, subject to the constraint that it doesn't exceed the budget. Okay? Now, of course, a feasible solution may not always exist, unless you, for instance, always add these dummy items. Okay? So we're going to see these models exist in the literature, in the computer science literature even. Okay? The point that I want to emphasize is that this can really be viewed as providing a spectrum between, encompassing a spectrum between pure social choice. For instance, if I have a very small budget, I may be only able to recommend a single item, right? Then I'm in the province of social choice, right? I'm recommending a consensus alternative. If I have a very large budget, I can recommend to everybody their most preferred item. I'm in the realm of pure personalization. And there's a whole spectrum of trade-offs in between, depending on how you're willing to trade off the budget or the cost of your alternatives with user satisfaction. Okay? Now, there are a number of special cases. I'm going to jump right ahead and talk about something called the limited choice model, okay? Where we assume that the fixed costs are 1, the unit costs are 0, and we've got a budget of k, okay? If unit costs are 0, that means anybody can consume whatever they want, okay? So they're going to choose their most preferred item from the set, So all I have to do is pick a set of k items and let users consume whichever they want, okay? This model, this limited choice model, is simply what Chamberlain and Courant developed in 1983 called the proportional representation system, down to the use of Borda scoring as a way of measuring representativeness or user satisfaction. Okay? So just to emphasize, there are a number of related models. Okay? Everything in multi-winner elections and committee selection and so on can be viewed as tackling this problem either in this form or in a variant form. Okay? As I've mentioned, proportional representation is a very specific instance of the budgeted social choice model, which we're calling the limited choice model, partly because we want machine learning people to pay attention. They're not going to pay attention if you talk about representative, proportional representation. Okay? But it is exactly the same model. Right? This model has been actually quite well studied in the literature, including computational properties. Ariel's done some work on that. Variants have been proposed that restrict the number of assignments to users so that we've got balanced representation, say, in a legislative body. And there have been even recent proposals that look at set-based notions of satisfaction that could be fit into this framework. What we want to point out is that by thinking of it in terms of a budgeted model, it gives you, which is something we don't believe has been explored in the social choice literature. It gives you the ability to really explore these trade-offs a little bit more, in a bit more of a fine-grained fashion. And I do want to mention, even though it hasn't been applied to social choice, that the general model that we proposed is really nothing but the model of segmentation problems that Kleinberg, Papadimitriou, and Raghavan proposed a few years ago. Okay. In the interest of time, I'm just going to skip very briefly through a few results. This idea that using a consensus ranking and picking the top K items won't lead to good slates of candidates. We can actually formalize that. For example, if we use border ranking and pick the top K elements, that slate can be as much as a factor of 2 worse than the optimal slate of candidates. And for arbitrary positional scoring, it can be actually, it can in fact be worse. Okay. And I mention this because a lot of work in the machine learning literature does come up with consensus rankings, and in their own form, and pick the top K items. Okay. Now there are a lot of ad hoc methods for adding diversity to recommended sets. Right. What we're proposing is don't make them ad hoc. Say what it is that you're trying to accomplish and optimize against it, or at least approximate against that objective. Okay. The problem is NP hard. Our result is marginally different than a result that Ariel proved a couple of years back for the limited candidate model. Sorry, the limited choice model. Can formulate it as an integer program, which people have done in the past. The nice thing is that it's amenable to a greedy approximation algorithm where we simply add candidates to our slate one at a time that improve the marginal societal benefit less. While here there is no cost, it's just the unit, it's just the slot cost, so to speak. It's not hard to show that this problem is submodular, and we get a ready approximation ratio, okay, of about 0.63. Okay. The greedy algorithm can be adapted to the general budgeted model, but without the same guarantees. Okay. Briefly, I'm going to skip this. Briefly, just want to show a few experiments. We've been looking at the performance of this greedy algorithm. The bounds aren't very, of the greedy algorithm aren't very tight, but it turns out it works really well in practice. So we've looked at it on a couple of data sets. One is the sushi data set, where we've got 5,000 full preference rankings over 10 varieties of sushi from a survey done in Japan. We did a bunch of experiments varying the number of options. So how many varieties of sushi can I put on the menu to make people happy? Looked at various scoring functions, Borda, exponentially decreasing positional scores, and so on. It turns out that greedy always finds the optimal from this particular, in this particular data set for all K and for all varieties of the scoring metric. Okay. Also turns out, despite the fact that in the worst case Borda can do poorly, it actually provides a pretty decent approximation. Kemeny provides pretty decent approximation as well. Okay. But the greedy algorithm is very fast, much faster than trying to solve this thing optimally. Okay, by a couple of orders of magnitude. We also looked at the more general budgeted problem, where we randomly generated some fixed costs for each variety of sushi and some unit costs, and set a budget so that in expectation there are going to be about 2 to 5 unique items that we could put in the menu. And again, greedy is always within 1 or 2% of optimal, and a couple of orders of magnitude faster than solving this thing optimally. Here we can't use things like Borda or other consensus notions because we actually have to find an assignment of sushi varieties to our users. Okay. The upshot is that this greedy approximation suggests that this model would be tractable. This model in the greedy algorithm would be tractable for largish data sets. All right, just to summarize, there's less novelty in this budgeted social choice model. These types of models have been explored, but haven't been applied to social choice in the way that we think they should. Okay. it generalizes the notion of multi-winner elections by explicitly using a budget to determine the representative capacity, so to speak, that you've got available, right? And again, it gets at the spectrum and addresses the trade-offs between pure personalized decision-making and consensus decision-making, okay? Fast, greedy algorithm works very well, and a number of interesting questions that I'll leave in the interest of time, okay? Now, I know it's 1 o'clock. Maybe what we can do, I'm going to skip all this. There are 2 slides for people who are interested and have time about sort of our broader research agenda. I wouldn't mind sitting down and discussing this with people who are interested for just a few minutes. But I know it's 1 o'clock, so maybe we can stop, allow people to leave if they have to, and maybe take a few questions. But I wouldn't mind taking a couple of minutes for people to stick around and talking about the last 2 slides. Okay. No. Yeah. Mm-hmm. Right. Uh-huh. Yeah, yeah. That's right. So, I mean, the way I view matching is normally it's typically one-to-one matching, right? And here, in some sense, we're assuming that here's a movie, but we get to decide how many users can take advantage of that movie or can play in that playground or something like that. That's maybe a little bit of a wrinkle. Uh-huh. Yes, right. Yeah, you're fair enough. Fair enough. Yes, that's right. Right. Very good. Okay. There are other connections to matching related to the unavailable candidate model that I think would be very interesting to explore as well. So we can talk about that because I know you have an interest in that model in particular. So, Ariel, yeah.
And back to the unavailable candidate model, you mentioned you want to look at incentive issues. I was wondering, so if you have P equals 1 for all the candidates, if that's the true situation, how all the voted people is, investigate reducing that to the more or less the normal social choice setting, and then give a cutoff rate and the voter results will kick in.
P equals 1 means nobody's available.
Sorry, P equals 0. So everybody's available.
Right. Yeah.
So then if everybody in particular reports P equals 0, then you get to the given coverage rate and the classic social choice model, and then the usual impossibilities will kick in.
Right.
So could you imagine?
Well, then the question is, what are the incentives for somebody to report or misreport these probabilities, for example? Right. So, there are a lot of subtleties in this question because if I ask a single person to report their probability estimate, right? Well, if they want to reduce this to a classical social choice problem that they can manipulate, then of course they'll say P equals 0, right? For example, right? But suppose I'm actually aggregating in the sense of an information market, for example, the subjective assessments of people for these candidate availability probabilities, right? Then what are the incentives for misreporting your subjective estimate, given some mechanism, hypothetical? I mean, I know they exist, but we haven't studied them in this context for aggregating the probabilities, right? Right, and then you've got to mix that with, with the preference reporting as well. That's kind of what I'm trying to get at. I don't have any idea how to begin to address that. Yeah. Probabilities. That's right. Yeah. That's what I'm trying to get at. Right. But I mean, that's a good point about if you rely on a single individual. Right. Yeah. Any other questions? Yeah, great, thanks. Okay, it's just really, you know, two quick slides that I want to talk about, right? Briefly, you know, I skipped over a couple of slides that kind of recapped what I viewed as some of the advantages of a decision-theoretic perspective on social choice, okay? And I know this sounds very utilitarian, and probably some social choice theorists would say that's not the right way to think about social choice. But I think in a lot of the computational problems that we're looking at, this is exactly what it is that we need to do, right? Set up a very specific objective, okay? Now, one of the advantages of having this very explicitly decision-theoretic view is that it can ease problems of elicitation, preference, and vote elicitation, and of learning people's preferences. So we know, for example, that communication of preferences can be very taxing. Got a large number of alternatives. Asking somebody to submit their ranking can be quite difficult, okay? In fact, that's influenced the design and acceptability of a large number of voting schemes, okay? Well, one question is, can you actually make decisions using incomplete information about people's preferences? In fact, this happens in statistics and machine learning all the time, where people develop algorithms to cluster various users and assess some notion of consensus ranking and noise parameters and things like this. What I'd like to consider is how one can use techniques from robust optimization. I've talked to a couple of you about this, in particular the notion of minimax regret to drive, first of all, to make decisions under vote uncertainty or preference uncertainty or incomplete preferences. And second, to drive the elicitation process, right? Minimax regret is a very, very simple notion to describe. Basically says, if I have an incomplete profile, I know something about your preferences, something about yours, but not everything, maybe in the form of just some pairwise comparisons or a top K list. If I propose a particular winner, I can ask myself, how far could that winner be from optimal given a worst case completion of your preferences, okay? And that we can only do if we have a specific objective function or decision criterion that we're trying to optimize against, okay? Not just the notion of consensus. And the nice thing about this, it will allow us to provide guarantees when we make decisions in the presence of such incomplete preference information, and it can provide guidance. Okay? These types of techniques have been used in single-agent preference elicitation quite successfully. Okay? Let me skip over a couple of points. The other thing is that given the real emphasis in the machine learning community on learning rankings and learning preferences, and the types of data that we're faced with, it's inevitable that we have to learn statistical models of people's preferences. What I would argue is that the focus on predictive accuracy, can I accurately predict a random user's preference ranking, okay? That may be misguided. And you're using a lot of, say, learning capacity to learn things that may not be relevant given a particular decision criterion. By deciding what it is that you're trying to optimize and what I'm going to do with these rankings, right? Produce the optimal case slate, for example. I can be much more informed by having optimization criteria that drive my loss functions. And that drive active learning, rather than focusing on predictive accuracy. Okay? And last slide, the idea of putting a little more nuance in the question of manipulation and incentives, I think can really be helped by taking this decision-theoretic perspective. Okay? Been a lot of focus on worst-case manipulation results in the history of computational social choice, dating back to the classic work of Bartoldi, Tovey, and Trick. Of course, these worst-case results, people say it doesn't have much meaning in practice. So recently, there's been a body of work that's looking at the empirical hardness or easiness of manipulating specific voting rules. But all of these formulations, at least the ones that I'm aware of, and if you know of others, I'd love to hear about them. Other formulations I'm aware of depend on the notion of manipulation as being defined in terms of, can I change the outcome of an election? Okay? But imagine that, you know, if I've got a plurality voting scheme, okay? And if a small coalition can change the outcome, right, from the winner from A to B, that means B had to be pretty close to being a winner in the first place, okay? All right, now if you have a large coalition, of course, all bets are off. And if you've done that, you might argue that you haven't really caused much damage. B was close to being a winner. Now in an election, right, Bush versus Gore, well, right, you've actually caused a lot of damage potentially, all right? But for the kinds of problems that people are thinking about in the machine learning community, the computational problems, you may not actually care. You may be more interested in the amount of harm or loss in utility, okay? And now, under such an analysis, when I think how much worse could the outcome be, it may well be, I don't say this with any confidence, but it may well be that things that we currently view as being very manipulable don't look so bad because the damage that can be caused might be very limited, okay? And others that are manipulable with very small probability, maybe the damage caused is very great, okay? So we get a more nuanced analysis of manipulability and incentives and things of that nature. And I think it's really important to begin to estimate, analyze these things relative to the kinds of empirical distributions that we see in practice, that the learning community is starting to put together, that statisticians who study rankings and permutations have been looking at for a number of years. Okay? And by the way, when we start looking at these types of questions, maybe certain schemes, even though you can prove they're not strategy proof, talking about Gibbard-Satterthwaite, maybe practically they become strategy proof given the distributions that the manipulators are going to be facing. Okay? So with that, I welcome any questions, any discussion of these things, because this is kind of a bigger picture that we have in mind, something that we'd like to begin to address, but we need lots of help. Well, I shouldn't say we want to address. We'd like to see addressed. Right? We know we're going to address it, but we think they're interesting questions. So, all right. Thanks, everybody. And apologies for the mix-up here. So, anyway, okay.